Well, hello. We're going to go ahead and get started with section 5.2. In section 5.2, we're going to consider measures of variation or spread. Okay then, let's go ahead and get started. In the previous section, we considered measures of location. In particular, we were looking at things such as the median or the average, the smallest, the largest. We also talked about percentiles. But here, in this section, we're going to be talking about measures of spread in data. So let us consider two situations here, situation 1 and situation 2. In the last section, we were looking at incomes across the state of Minnesota. This top picture is what we had there. So you can see that the smallest county, or the poorest county in Minnesota, had income levels at about $35,000. And the richest county had income levels upwards of $85,000. And actually, there's a couple of counties up there, it looks like. Most of the counties are, most of the counties are in that 45 or maybe 44 to 54,000 or so, are in the 45,000 to 55,000 range. And this plot here, okay, it has the same average, so the average hasn't changed here, but you can see that the points are all much closer together. And that characteristic in the data is the variation in the data, or the spread in the data. So in situation 2, the incomes are all very similar across the board, I guess, or all the counties have very similar incomes. All counties have similar income levels. Okay, now there are a variety of terms that are used in place of the word variation or in place of the word spread. Okay, it's not like the measures of location, average and median are pretty well set, but we don't have that same terminology for everybody across the board when we talk about variation. So sometimes the word disparity gets used. So if a state has high income disparity, that means the incomes are dissimilar. If you're in business, a lot of times they'll talk about volatility in measurements. Volatility is the sense of variation. Okay, so if stocks are very risky, they'll have a lot of volatility in them. And again, what they're talking about is variation there. Another word that gets used sometimes is dispersion. Statisticians usually refer to this concept as variation, though. That seems to be our go-to word for this. Okay, so let's talk about some measures of variation that exist. The first is the range. The range is easy to compute, certainly easy to understand, but it's very limiting in the information that it provides on a set of measurements. Okay, so practicing statisticians don't actually use the range very often at all. So what is the range? Well, the range is just simply you take the maximum value in the data set and subtract the minimum value in the data set. So for our Minnesota income data set that we've been looking at in the last section, continuing with that, the maximum county was at $83,000 for household income. The poorest one, or the smallest, okay, was at $35,000. So that range there is just take the $83,415 and subtract $35,307. You get a range of about $50,000. So again, the amount of span between the poorest county in Minnesota and the richest county in Minnesota is about $48,000. Now, as I just said, the range is not a commonly used measure of variation by statisticians. Now, the range is a common measure that is out there because it's really easy to compute. Okay, but it's not one that statisticians use on a regular basis. There's two main reasons for this. First of all, it only uses 2 observations in the entire data set. It uses the largest observation and the smallest observation. Now, if I were to ask you to compute the average, okay, you wouldn't use only 2 of the observations to compute the average. Okay, so we advocate that you wouldn't want to use only 2 observations to compute the range, neither. And also the range, by definition, is adversely affected by outliers. So it is using the largest value on the right-hand side, and it's using the smallest value on the left-hand side. Well, if I have any outliers in my data set, they're either going to be extreme on the right-hand side, or they're going to be extreme on the left-hand side. So by definition, the range is messed up directly by outliers. And for those 2 reasons, the reasons that it's messed up by outliers and that it only uses 2 observations, are the reasons we don't consider the range a very good measure of spread for a set of measurements. So let's go ahead and take care of these questions. I think we answered those already, but how many observations from a data set are used to compute the range? So only 2. Only 2, the largest and the smallest. What is the smallest possible value for the range? Okay, we didn't talk about that yet. Well, if the range, how small can the range be? Well, if the top measurement and the bottom measurement were the same, then that difference would be 0. Okay, so maybe let's look at that up here in this plot. The range in situation 2 here is going to be a lot smaller than the range in situation 1. In fact, the smallest possible value is going to be 0. Okay, so if all of the data points are exactly the same, suppose all of the counties had incomes at $50,907. The largest would be at $50,907, and also the smallest would be at $50,907. So the range there would actually be 0. So the smallest possible value for the range is 0. Okay, so the smallest possible value for the range is 0. And this just means there is no spread in the data. All the data points are exactly the same in this situation. So as the range gets smaller and smaller and smaller, it means that the data is becoming more and more and more alike. Oops. Okay. Actually, it just means that the largest value and the smallest value are becoming more and more alike. Okay, let's talk about this other idea that John Tukey came up with. John Tukey knew that the range was not a very good measure. John Tukey is the inventor of a box and whisker plot, or a box plot. And he had this idea called the interquartile range. And what the interquartile range is about is that you're just going to lop off or cut off or truncate kind of the lower end of the distribution and the upper end of the distribution and just compute the range of what's left. Okay, so how much did he lop off on the left side and the right side? Well, he wanted to make sure and lop off all of the outliers on both sides, so he ended up lopping off 25% of the data. Okay, and this is built on the idea of a box plot. Okay, a box plot just takes our data, and divides it into 4 quartiles, 4 different quartiles. The bottom 25%, the 25 to the 50th percent, the 50th to the 75th, and then also the top 25%. Okay, so the interquartile range is just the range of this box plot, the box itself. So how far do I go from the lower end of the box up to the upper end of the box? Okay, so this idea actually stemmed from the creation of the box and whisker plot. So for this particular data set, okay, the 75th percentile, okay, which is called the third quartile, is at 52,500 or so. Okay, so 75% of the data sits below that point. And then I also have the first quartile. The first quartile is at 44,820. Okay, the first quartile means that 25% of the data sits below that point. Okay, and I just compute the range of those two quantities. So I take 52,500, subtract 44,800, and I get about 7,700 or so. Or about 7,800, I guess, if I round correctly. And that is giving me an indication of how close together the middle part of the data is. Okay, not the entire data set, but just this middle portion of the data. So how is the data condensed here in the middle? The interquartile range will allow me to measure that. Okay, so that's a neat idea. However, other than its use for the construction of the box and whisker plots, we don't use the interquartile range very often as a measure of spread. Okay, so it's definitely used when we create the box plots, but it's not used as an independent measure of spread very often. So what do we use then? Well, we use this idea of distance to the middle. Remember, if we go back to the chi-square tests, the chi-square test was an evaluation of how close the observed data was to the expected data. And we use that same idea here when we're measuring variation in data as well. Okay, so let us consider 3 data sets here. Data set A, data set B, and data set C. And this is just data from Rhode Island. I used Rhode Island because Rhode Island has 5 counties. Okay, and this is just fictitious data for Rhode Island. But data set A, let us suppose that Rhode Island has all 5 counties in Rhode Island all had the same income, and they were all at $50,000. Data set B, I have 3 counties that are at $50,000, but then I have one down here at 30 and another one at 70. And then data set C, I have those kind of dispersed equally between 30 up to 70,000. So I have one at 30, one at 40, one at 50, one at 60, and one at 70. And we ask what distribution or what set of measurements are more spread out than the others. Certainly, I think we could agree that data set A has the least amount of spread because all of the data points or the incomes from these 5 different counties are exactly the same. So data set A has less spread than either of the other 2 data sets. But let us consider data set B and C. Which of these 2 have less spread? Now, if we were to use the range would indicate that the spread is the same between the 2 because both data sets go from 30 up to 70,000. However, the spread is different between data set B and C. We can see that the data is different, and in fact, data set B has more clumped in the middle compared to data set C. So we would say that data set B has less spread than data set C because it has more observations that are clumped in the middle. And again, this is based on the fact that we measure spread as distance to the middle. So let's talk about that distance to the middle. We actually have a name for that quantity, and it's sometimes called the residual value or the deviance value. And that deviance value is just, again, the data point to the average. So how far away is the data point away from the average? The average in all 3 of these displays is at $50,000. So the residual here for this particular point at 30,000, I would just take 30,000 and subtract 50,000. So the residual value here for this particular data point would be at negative $20,000. The residual value for this value, the value at $70,000, the residual value would just be 70,000 back to the 50,000, so that'd be $20,000 as well. The residual for this point is negative, and the residual for this one is positive. So if I'm at a positive residual, that means I'm above the average. And if I have a negative residual, it means that I'm below the average. So again, this next picture on page 21 is just showing you those different residual values. So on data set A, each of the values is right at $50,000. So I don't have any residuals for any of the values. Okay, for data set B, I have one residual at negative 20,000, and I have another residual at positive 20,000. So down there on the low end, down here on the low end, I'm 20,000 away, And up here on the upper end, I'm positive 20,000 away. On this one here, I have data set C. I have one residual at negative 20,000. I have one residual at negative 10,000. I have a residual at 0 there. The middle data point has a residual of 0. And then I have a 10,000 and a 20,000 as well. Now, when I sum these up, just like what we had before, when I sum these up, I end up with zeros here. So the total here is 0. And it's 0 in all of those cases. Now, again, we ran into that when we were looking at the chi-square test as well. And the reason that is happening is that these positive residuals, okay, so this positive residual right here is being canceled out by that negative residual there. So just like when we talked about the chi-square test, we're going to have to do something to get rid of those negative residuals or get rid of the canceling out effect that we have. And the two ways that we did that were either using the absolute residual or we did the squaring of the residual. So here, I'm showing you in the bottom of page 21, I'm showing you the absolute version. So here I can just take the absolute value of the residuals. So at this negative 20,000 here for data set B, let's go ahead and look at that one. At negative 20,000, the absolute value of that is just 20,000. Take the absolute value of positive 20,000, I just get back 20,000 here. And now notice when I add those up, when I get that total, okay, when I get that total, I don't get that canceling out effect. So for data set, what is this? Data set B, I guess, for this one right here, the total distance away from the middle is 40,000. I got 20,000 on the left side, 20,000 on the right side. So on average, how far away are the data points from the middle? Well, to do that, all I would need to do is just take that 40,000, that's the total distance, divide by the 1, 2, 3, 4, 5 data points. Okay, that's what I do here on the bottom of page 21. I just took the total distance and divided by 5. So on average, in data set B, the observations are about 8,000 away from the average, or from the middle of the data. Now with data set C, if we do that same thing, I'm going to have the negative residual here at negative 20,000. Okay, but I'm taking the absolute value of that, so that's positive 20. So here I'm going to have 20,000 plus 10,000 plus 10,000 plus 20,000 plus that point at 0 there. I didn't have any for that one. So that's going to be, what is that, 60,000. So the total there is at 60,000. Again, I have 1, 2, 3, 4, 5 observations for Rhode Island. So 60,000 divided by 5 is 12,000. So for data set C, we tend to be about 12,000 away from the middle or the center. So let's just recap here. For data set A, I'm 0 away from the middle on average. Data set B, I'm 8,000 away from the middle on average. And data set C, I'm about 12,000 away on average from the middle. So using that approach, we can see that data set C tends to have more spread or more variation than data set B. And certainly both of those have more variation than data set A. Now that measure that we just talked about is the mean absolute deviance, or the MAD value. Okay, so that's one acceptable measure of spread that we statisticians use. And that one again is based on just taking the absolute residual value, or the absolute deviance value. Now, how about the squaring approach? The squaring approach does something similar, except that it takes those residual values and squares them instead of taking the absolute value of them. So here I have the negative 20,000, and I square that. I actually get a pretty large number here. I guess that's 400 million. So when I take 20,000 and square it, I get 400 million. On the other end, for the other residual, I'm going to take positive 20,000 and square that. I'm going to get another 400 million. And when I add that up, I get 800 million. Okay, and if I divide by the number of observations, I'm going to get 160 million here. Now we can see that one problem with the squaring is that the scale gets really messed up here. These data points, okay, let's go back here and look at the graph, are not 160 million away from the middle. Okay, so what has happened here is that my squaring has messed up my scale on me. These numbers don't really make sense anymore. These numbers are correct. I mean, I did the math correctly here, but they just don't make sense in the context of the measurements that we have here. We're talking about dollars here. Okay, so the units of measurement here, I guess, would be dollars squared or something. Now, we do see that data set C does have a larger value, okay, does have a larger squared average value than data set B, which is what should happen because we have more distance away from the middle in data set C than in B. Okay, so this is based on the squaring the residuals here. And we call this approach the variance approach. Now, one thing that we have to do here, well, a couple of things, I guess. One thing that we end up doing is instead of dividing by the number of observations, 5, we actually divide by 1 minus the number of observations. Okay, so we actually divide by, if I have 5 observations here, would be dividing by 4. Okay, and again, that has to do with the number of these residuals that are free to vary. Okay, when we are doing these calculations, it's closely tied to the notion of the degrees of freedom that we talked about back when we were looking at a chi-square test. The other bigger problem, okay, so with a large number of observations, to be honest, it doesn't really matter if you divide by n or divide by n minus 1. Here in this fictitious data set, it actually will have a pretty substantial impact because I only have 5 measurements. But in reality, oftentimes it doesn't really matter if you're dividing by n or n minus 1. But the bigger problem is that the scale is messed up. Okay, I did this squaring to get rid of the negatives. Well, I probably am going to have to take a square root to undo that problem. Okay, so taking the square root of the variance is actually called the standard deviation. Okay, so let's just think through this a minute. What is the variance? Well, the variance is the average squared residual value. Okay, it's the squared residual value. And that's not on the right scale for the data, so I need to take the square root of that to bring it back onto the correct scale. So now when I do that, for data set B, I need to take the square root, okay, of this 200,000, or 200 million, excuse me. And when I take the square root of that 200 million, I get about 14,000. So the standard deviation for data set B is at about 14,000. The standard deviation for data set C is at about 15,000 or pushing 16,000. So again, data set C has more spread, okay, than data set B, as indicated here, with a difference of about $2,000. Now the measurement scale for the standard deviation is dollars, okay, because I messed up the scale by squaring, but I square rooted that, so I brought it back onto the dollars scale. So that's the description of standard deviation. And this one, the standard deviation, is actually more common than the mean absolute deviation, where we're using the absolute value. And the reason that is because of the mathematical properties associated with the standard deviation, okay, which is beyond the scope of this course, but there's advantages to using the standard deviation. Now some comments here about these measures of spread. The range should not be used to measure spread. I think I talked about that enough up above. The mean absolute deviation or the standard deviation are acceptable ways to measure spread. The standard deviation is the most commonly used measure by statisticians, again because of its theoretical properties. The mean absolute deviation and the standard deviation cannot go below 0. So a value near 0 implies less spread. Okay, it's like the range in that way. So values close to 0 imply less spread. And if I have a larger value, then that means I have more spread. Also, measuring distance to the middle is different than a uniform pattern in the data. So sometimes students think that data that looks like this, which is real uniform in pattern, actually doesn't have much spread. And what they're doing when they're looking at that is just the gaps between them. The gaps between the observations are pretty consistent. But again, the way statisticians measure spread is distance to the middle, not gaps between the observations, but distance back to the middle. And that's what both the mean absolute deviation and the standard deviation are based on. We can get these quantities real easily in a spreadsheet. Okay, if we want the the mean absolute deviation, I just use the equal AVE DVE function. I just did this on a little set of measurements that we were looking at. The standard deviation, I just use equal STDEV, and then again highlight the data that you want to compute, which here I just put that here. In the last section, I showed you how to name a range of data in a spreadsheet. You can do that here. If I were to name the range, let's say name this range incomes, then I could just use equal AVE DVE and then put income in here, and I wouldn't have to worry about highlighting the different cells. In the last section, we looked at the income disparity issue in Minnesota, Wisconsin, and Virginia. We had this dot plot. And now I actually have a measure for income disparity, which would be the standard deviation. Again, the standard deviation is just measuring that average distance back to the middle. Virginia, because it's so much more spread out, is going to have a much higher standard deviation than Wisconsin, for example. The Wisconsin counties are all bunched together pretty good in terms of income. So their standard deviation is going to be low compared to Virginia. And if we want to compare those values, Wisconsin has a standard deviation, which is again the average distance to the middle, of about $8,000. Whereas Virginia has an average distance to the middle of almost $20,000, or a little over $19,000. So the measurements in Virginia are a lot more spread out than the measurements in Wisconsin. And again, that was the income disparity things that we talked about in the last section. So the income disparity is much higher in Virginia than it is in Wisconsin or even Minnesota. Okay, let's go ahead and take care of these questions. Does the fact that these states have a different number of counties adversely affect our ability to make comparisons? Okay, and the answer to that is no. All right. So this is a common misconception about making comparisons. The number of observations, the number of data points does not, or at least should not, maybe I should say that. Let me just say the number of data points does not mess up the commonly used measures of location and spread. Actually, any summary measurement. Okay, so the number of observations do not mess us up. Sometimes students believe that the number of observations need to be the same before I can make comparisons, and that's not true neither. Some students believe that if I compute a standard deviation when I have lots and lots and lots and lots of data, then that's going to be really, really, really large. And that's not true neither, because a standard deviation is an average. It's an average distance to the middle. Or even the mean absolute deviation is an average distance to the middle. So even if you have lots and lots and lots of data, we're computing an average here. We're dividing by the number of observations there. Okay, so that's being accounted for in any measure that we statisticians use. Okay, any commonly used measure that statisticians use, it's not messed up by the number of observations. So number 4, how does the average income compare across these 3 states? Okay, these are pretty even in terms of average. Okay, we talked about that actually in the last section a little bit. You can see that from the CDF plot, the median here. Again, if you go across at the 50th percentile, that's the median, and drop down. Again, all of those are right around 47, 48, 49,000 or so. How does the spread in income vary across these three states? There we have a pretty substantial difference. Okay, so Virginia has much more spread, which is more income disparity, than Minnesota and Wisconsin. This can be seen by the standard deviations and also seen in the CDF plot below. So again, the steepness in this plot is indicating spread. So does the appearance in this plot agree with the answers in 2 and 3 up above? I think it does. Let's just go ahead and finish this one out. Oops. So yes, the medians are the median for all three states are pretty similar. So again, go across at percentile equal 50th and drop down. They're all similar, near 50,000, I think we said. Also, the steepness for Virginia is Virginia is the least steep, I guess, which means most income disparity. And this is true. This is true from the standard deviation calculations as well. Standard deviation 19,000, which is much higher than Minnesota and Wisconsin. Okay. That does it then for section 5.2. Thank you very much, and until next time.